So as we move forward, we're going to get into solving systems of equations. So looking at these two equations, these are actually linear equations. They're two variable equations, degree ones. So if I was solving this system of equations, one way I could do it would be to graph it, and the intersection would be the solution. It would be unique. So keep that in mind. We're going to be working with uh, two variable equations that are lines. So when working with these two variable equations, there can be infinite many solutions, and those can be, like I said, represented with a line. So if we just graph a single line, there are many, many points on a line. So the only way really to describe the solution is just draw the line. But now, if I'm working with a system of equations, like I said, there's two unknowns exist. So if there's two unknowns exist, there needs to be two equations in the problem. If there are three unknowns, we would need to have three equations if we're talking about a system of equations. If there were four unknowns, then we would need four equations if we're talking about a system of equations. Luckily, for our purposes, we're just going to work with two variable equations. So our systems will only have two equations. So this is kind of the beginning of systems, if you will. So since these equations represent lines, we have three different scenarios. There can exist exactly one solution, which would be an ordered pair. And what that would mean is the two lines intersect, and this would be the intersection point. In solving a system of equations, there could also be no solution. And graphically, that means the two lines are parallel and there's no points in common. So a system of equations could also have no solution. And if you graphed it, what that would imply is there is no point of intersection. The two lines are parallel. The third scenario, if you're solving a system of equations, there can exist infinite solutions. This can be represented graphically as the lines are coincident. What that means is they lie on top of each other. The solution itself would be the equation of the line, and it would represent the set of infinite ordered pairs. So when I'm solving this system of equations, what we want to do is figure out a strategy. One of the strategies we can use is what's called the addition method. So the addition method is what we want to do. If I'm using the addition method, we want the equations to be in standard form. So let's see if we can bring these down here. Let's see here. This thing's in the way. Yeah. So if I want to solve the system equations using the addition method, we want the equations in standard form. Also, we want them to be on top of each other like this. So this looks perfect. So if we have a minus 3b equals 7, and 7a plus 3b is equal to 1, this is perfect to solve using the addition method because remember, standard form is this ax plus by is equal to c. So the variables are on the same side, the constants on the other. This is perfect. So this is where standard form becomes really, really good in working with what we call systems of equations. It's not great for graphing necessarily, but it is great working with systems. So one of the things we want to do in the addition method is once the equations are in standard form, what we want to do next is this. If necessary, multiply one or both of the equations by numbers that cause the terms of one of the variables to add to zero. So if I look at this, we want to add these two equations together. But what we want to do is we want to add in such a way that one of the variables disappears. So if you look right now, if I add 7a plus, if I add a to 7a, does that variable disappear? No, that turns into 8a. But if I look at the b's, does negative 3b and 3b add to zero? Yeah. So notice that what we want in the addition method is we want the coefficients to be the same, but we want them to be different in sign. If the coefficients are the same and different in sign, that means they will drop out of the problem and allow us to solve for one of the variables. So now we want to add the two equations together to eliminate a variable, since this is already perfect for the addition method. So we're going to just add 1a to another 7a's, that's 8a. This drops out, and then 7 plus 1 is going to give me 8. This enables me to solve for a. So if I now divide both sides by 8, you can probably see the answer, though. You don't really need to do that, because 8 times what is 8? Well, that would have to be a 1. So notice that a would have to be a 1. So we now have solved one of the equations. So we solved the equation for the remaining variable. Now what we want to do is we now want to substitute this answer into one of the equations at the beginning somewhere. So what we want to do is return this value of 1 back up into these first two equations. Which one looks easiest? It's just your preference. I really don't like to see the subtraction symbol, so I'm going to go ahead and use the second equation. Doesn't really matter. You may want to say, I may want to go back to this first equation. So, eeny, meeny, miny, mo. I'm just going to go ahead and pick the first one. So, what I could do now is substitute the 1 in for a minus 3b is equal to 7. So now what I can do is solve for b. So I can get rid of this 1 by subtracting 1 to both sides, if you will. Use my property of equality. So that gives me a negative 3b, and 7 lose 1 is going to be actually a 6. And then I got to make this coefficient of negative 3 turn to 1, so I have to divide it by itself. So I divide by that coefficient. So that gets my b by itself. So if I can divide 6 by negative 3, well, that's a negative 2. We've done it. So a equals 1, b equals negative 2. If I want to write that as an ordered pair, your ordered pair would be 1, negative 2. So that means there is just one solution. If there's one solution, sometimes we call this consistent and independent. So we have a little name for that as well. That means there's one solution.